around the black hole. Okay, yeah, please start.
Okay, I'm Hsiao. I'm a first-year master's student from National Tsinghua University, and I'm going to talk about this interesting research called Dyson sphere around a black hole. So first of all, I will give a brief introduction about some terminology like what is Dyson sphere, and then we will go through the energy source, what we can extract from the black hole, then discussion and the conclusion. So let us start. So, a very early stage of human beings, our ancestors have already imaged the existence of the aliens, and this phenomena also reflects on the media nowadays, such as sci-fi movies, and the search for extraterrestrial intelligence and has been conducted since 1960s. So this is also known as SETI. They try to use the infrared signal to receive the signal from the alien or communicate with them. Then the first exoplanet has been discovered for 30 years, which opened another new window for searching the aliens. But somehow there's only negative results so far. And scientists divide the civilization into 3 categories based on their energy consumption. So type 1 civilization is to use the energy from a planet, and type 2 civilization is to harvest the energy from a star, and also type 3 civilization is pump all of the energy from a galaxy. And we caution the audience that this is just the criteria for type 1, 2, 3 civilization. And later, the Kardashev proposed an index to set the norm to measure the civilization. So by interpolation and based on their energy consumption, does anyone want to guess about the K index of our human beings?
1.
1.
0.1.
0.1. Okay, so the answer is 0.733 based on the energy reports last year, 2019. But how to solve the energy problem in the future, because the energy consumption will increase day by day and year by year. So Freeman Dyson, a famous scientist, established a concept called Dyson sphere, and it's a spherical structure which floats around the star and intercepts all the radiated energy outward. And this is the imagination of the Dyson sphere by artists. Then, because in reality, to build the rigid Dyson sphere is somehow mechanical impossible due to like the gravity and the inner pressure. So there are many variants. So I just listed here. I'm not going to talk about this in detail. Dyson swan and Dyson bubble. Then this study is into what? And first of all, we assume a civilization between type 2 and type 3 civilization. We call it the alien, but it can also indicate Earth in the future. And they must have already harvested the energy from their parent star, like our sun. So next step is to search for nearby star or the black hole to extract the energy. That's what we want to know. Then, if the alien have built the Dyson sphere, could we detect it like this related to SETI? So this is the Dyson sphere around the star or around the black hole. So we go through the energy source. First is cosmic microwave background, and just brief introduction. This is a remnant of the Big Bang, and the temperature of the CMB is 2.7 Kelvin based on the black body radiation spectrum. And you can notice that the theoretical model fits very well with the observational data. And Avilov suggests that the habitable universe starts when the temperature of the CMB is around 300 K. But you may wonder, we discussed about the Dyson sphere around the black hole rather than around the whole universe. Why CMB? So for most of the cases in the universe, CMB is hotter than the black hole. So actually, we cannot extract the energy from the black hole itself. So we turn the idea of the Dyson sphere upside down. So something like this. This is the original concept of Dyson sphere. We absorb the energy from the center star and emit the waste heat radiation into the background. Then we turn this concept upside down. So we collect the energy from CMB and emit the waste heat into the black hole. And this is our results, the power as function of CMB temperature and black hole mass. You can notice that this curve is type 2 civilization is one solar luminosity. So for a recent universe, it's most impossible to find a supermassive black hole to reach type 2 civilization. So it's somehow not efficient to harvest the energy from CMB. So we discuss next energy source, Hawking radiation, which is the counterpart of the first one. And this is the radiation of the black hole itself. And this is the formulation. And I'm not going to talk about this in detail, but this is actually very low. You can notice that it's 10 to minus something. And if we want to extract the energy from the Hawking radiation, we need to find the black hole mass smaller than half of the moon. Because if we find the black hole is larger than this value, the temperature of the CMB will be actually hotter than the black hole, so we cannot extract the energy from the radiation of the black hole. Next one is accretion disk. So accretion disk is something accreted by the massive object around in the center. And this is, we assume this two formulation. And this is imagination concept by artists as well. And this is our results. You can notice that for stellar black hole, the Eddington limit is around 10 to 5 luminosity. It's almost 5 order larger than type 2 civilization, which is 1 solar luminosity. And for supermassive black hole, you can notice that it's covered around type 3 civilization. It makes sense because supermassive black hole is one of the biggest energy source from a galaxy. It's what is the definition of the type 3 civilization. Then the relativistic jets is one of the high energy and piercing phenomena in the universe. And it's believed to be driven by the tangled magnetic field. And a nature paper suggests that there's an empirical relation between the luminosity of the jets and the luminosity of the accretion disk. The result suggests that the luminosity of the jet is slightly larger than the luminosity of the disk. And the total energy from the jets is believed to 10 times of the larger than the luminosity of the jets. And you can notice that this is the same thing, and this is jets from the black hole along the rotation axis. And then we go through this result. I will discuss the real value later, so just show you the results fig, and you can notice that for mass black hole is almost many orders larger than type 2 civilization. Yep. Then next is discussion. So how much energy we can get from the black hole? So we discussed two scenarios, and with the Eddington ratio is 0.1%. I'm not sure here, but you can notice that even in the low Eddington ratio for stellar mass black hole, it can also boost the K index into 2.44. And for supermassive black hole, it exceeds the type 3 civilization. Which, if this case, you want to collect energy from 6,000 of the star in main sequence, or just find a stellar black hole and collect the energy from it. Yeah. So we also discussed what we can really measure from the sky. So we discussed this multi-color spectra from the accretion disk. So this is the black one is black hole, and yellow one is the accretion disk. So we divide this into many layers and assuming different temperature profile. So we use this formulation to integrate the black body radiation from this accretion disk. So if we can really measure the Dyson sphere, so we assume this configuration, say stellar mass black hole and 0.1 Eddington ratio, and eta is the transfer efficiency, and RC is the coverage fraction of the Dyson sphere. Say it covers the half of the sky of the black hole, and D is the distance between the observer and the black hole. So you can notice that there's a normal peak. In the longer wavelength, it's around ultraviolet. And if we enlarge this peak, we can notice that this radiation from the west heat is actually detectable. So next, we assume a wide range of these parameters. Sorry for the low resolution. But you can notice that the shaded region is most possible to detect the Dyson sphere. And this is the peak wavelength of the west heat from black body radiation. And you can notice that for stellar mass black hole, the most possible to detect this kind of structure is using UV. And if we want to find the Dyson sphere around supermassive black hole, we need to use UV optical near infrared to mid infrared. So if the area have already do the Dyson sphere around a black hole, either in stellar black hole, intermediate black hole, or supermassive black hole, we can use this wavelength telescope to detect it. So I leave the conclusion remarks here. So thanks for listening my talk. Hope you enjoy it.
Thank you very much. Any question? Okay, I don't see any question.
Oliver, have a question?
Yeah, please.
I saw in one of your PowerPoints that you assume that the receiver of the Dyson sphere have a distance at a scale about 1,000 kilo per second from the back.
10,000 kilo per second is 10 kilo per second is the Dyson sphere, and the Earth, the distance between this one. Yeah, it's not the radius of Dyson sphere. Yeah.
I have a next question.
Yeah.
Well, if your energy receiver is close to the black hole,
yeah,
then we know that the time near black hole is more slower. Then could it affect the energy efficiency in this aspect?
It should be. Yeah, but we didn't discuss in this study. Yeah.
Any other question from local or distant? Okay.
It's actually me.
Okay. You can. Yes. Yeah. Sure.
So when you compare accretion disk and wasted energy,
yeah,
if there's a dust torus, then that overlaps with the wasted energy?
Actually, if I remember correctly, the dust torus is emit around infrared.
Yes.
So, yeah, actually it's a little bit overlapped, but I think for Dyson sphere the wavelength will be a little bit shorter.
So somewhere in the middle.
Yeah, right. Yeah, if one day in the future we can detect this abnormal features, we can discuss about these parts. Yeah, maybe this not from the some physics, maybe this real from real Dyson sphere. Yeah.
You can ask Dennis to include this wasted emission in Hsiao.
Yeah.
Not just polar dust in Dyson sphere.
Yeah, we can try.
Thank you.
No, actually, I mean, if you have any ideas, it's possible to add something. But well, we need to formalize this, but why not?
Thank you.
Thank you. Okay. Any other question? Quick question? From local? Okay. Okay, if not, yeah, let's thank the speaker again.